So essentially every secure system that we use, and basically all the cryptography that those systems are built on, somehow relies on being able to generate random numbers. And yet most of the time, we're left asking, like, where are they coming from? Do they just appear from the ether? And when they do, are they good? Are they bad? So in fact, this problem gets even harder under the unique constraints of embedded systems. And so this is why my co-authors and I designed this hardware and software system for generating random numbers that's tailored to the embedded context. So in particular, we built some hardware that costs about $1.50, and it takes up about a square centimeter and a half of board space. This is for our prototype. And it uses about as much energy as sending 10 Zigbee packets, and yet you get randomness for the whole life cycle of your device. So in the rest of the talk, I'm going to tell you a little bit about what makes random numbers good or bad, why embedded systems are particularly challenging, and some of the design decisions that we made to kind of overcome this. So what happens when our randomness is bad? Well, a famous example of a randomness-related failure is from the Debian Linux distribution. So a few years ago, there was this bug, and the result was that if you were subject to this bug, and you almost certainly were because it was there for 2 years undiscovered, then any secret key you generated on your system was easy to guess. Like, there were one of 32,000 possible keys that anyone could have. So, I mean, this is an impossibly bad failure, right? And yet, it was undiscovered because, well, I mean, things kind of look random, right? So, okay, so clearly bad randomness is bad, but what is good randomness? Well, okay, so Randall Munroe's definition of good randomness probably is not the definition we want. But let's not give up yet on determinism as a way of getting, well, at least pseudo-randomness. So if we were going to build a pseudo-random number generator, what properties would we need it to have? Well, one thing that seems useful is we want the output of the pseudo-random number generator to be uniformly distributed. So as an example of a uniformly distributed pseudorandom number generator, consider the GNU libc's rand function. So this uses a linear congruential generator, and the output is very close to uniform. And yet, this isn't going to be good enough for security. The reason is that, look, if I see a few outputs from that generator, then I can predict all the future outputs, because all of those outputs are linearly related to one another. So, okay, that's no good, because now I can guess all of your keys again. All right, so let's try again. What else could we add to this? Well, imagine that we want to say, well, okay, it's uniformly distributed and there's no self-correlation in this way, so now maybe I can't figure out what your keys are. So an example of that is, imagine that as your random number generator, you just use the digits of pi. So you say, I ask you for a number, you say 3, 1, 4, 1, I can't remember the rest of them. Well, okay, so that seems like it's okay, and actually it turns out that that will pass essentially any statistical test that you can throw at it, and the reason for that is that pi has this weird property called normalness, or normalcy, where the digits of pi actually do look random in some really deep way. But, again, this isn't gonna work, because as soon as you figure out that I'm generating digits of pi, you're like, oh, okay, well, he's on the 15th digit right now, so then you can just generate the 16th digit, and again, no good. On the other hand, there is something here that maybe we shouldn't throw away. And remember I said, if you know which digit I'm on right now, then you can predict the future ones. But what if you don't know? What if there's some secret in there? And so here's the idea. We're gonna have a deterministic algorithm, but we're gonna have a secret added to it. And in fact, this is a totally standard thing in crypto. It's called a cryptographically secure pseudo-random number generator. And the idea is, we have a deterministic algorithm, and we have a secret key. And we have some, informally, some property like this. If you've seen every past output of this generator, as long as you don't know what the key is, there's no way you're gonna be able to predict any future outputs. In particular, there's no efficient algorithm that can compute what the future outputs should be. And now the next question is, okay, well, how can we build such a thing? Well, it turns out that under reasonable assumptions like AES is secure, we can build it. And in fact, if you have a secret key and you just encrypt the sequence 0, 1, 2, 3, 4, 5 under AES, that's it, you're good. Because of the properties of AES, that is a secure pseudo-random number generator. So in particular with AES, we can generate something like 1 billion gigabytes of data before we have to choose a different key, which means we only need like 128 bits of a secret key in order to generate essentially as much randomness as we could ever want. All right, and on top of that, we can make a strong statement about the security. So as long as AES is secure, then the only way that you'll be able to guess what my future outputs are is to guess what my key is. Okay? And this lets us come up with this metric, entropy, or guessing entropy really, where if I have a secret key, you have to guess the bits of the key in order to figure out what my future output is. All right, so now we kind of have an idea. This is what we're gonna go after. We're gonna be able to generate strong pseudorandom numbers for use in crypto by using a secret key and a cryptographically secure pseudorandom number generator. And so the question is, where do we get this secret key from? Well, surely today there are solutions to this. And in fact, there are. So in traditional systems like your desktop or your laptop, your operating system is constantly running this process to gather entropy from sort of unpredictable events. Like, for example, the hard drive timing, or maybe your keyboard interrupts, or network packet arrivals, things like this. But unfortunately in embedded systems, well, we don't have many of these things, right? There's no keyboard attached to the moat that's on the wall, and so there aren't these sources. And even if we did have such sources, there would still be a problem. Because look, now we're gonna have to be constantly gathering little dribs and drabs of entropy from these things, and so really spending energy constantly to try and get enough entropy to securely generate random numbers. So there's another approach that's increasingly becoming an option, and that is a lot of processors and systems on chip now have these embedded hardware random number generators in them. And this seems great. Actually, as an example, I think I put up here, yeah, RDRAND on the Intel processor. I think a lot of people are familiar with that. So this is great, except, look, if you've already selected your embedded processor and it doesn't have one, then you kind of missed the boat. But probably more importantly, many of the manufacturers who put these things in the chip, they don't give us any kind of guarantee about what they do. They say, here's an instruction, it'll give you something random. That's it. So I don't know if it's gonna be easy to guess, I don't know if it's gonna be hard to guess, maybe over temperature, or in 5 years everything fails. Hard to know. And beyond that, it turns out that it's actually quite easy to backdoor these random number generators in a very subtle way. So in 2013, Becker et al. Showed that with a couple changes in the dopant in the Intel random number generator, they could make it put out something that was very guessable, and yet it would pass all the statistical tests and it would be essentially impossible to find. So look, so all of these methods seem like they fall short. So this kind of gives us an idea now. Let's try and write down what is it that we want. Well, okay, so clearly we're gonna have to pay for the thing. So we want it to be relatively inexpensive. We don't want it to take up too much space, and we don't want it to use very much energy. Another important requirement is that the circuit needs to work even if the temperature changes, or over time, 5 years from now, everything still needs to work. So we want something that's insensitive to things like temperature, radio frequency interference, and this sort of thing. And look, all of our system security, as I've argued, is relying on this. So that means we need to be able to detect if it fails. So what we really want is a circuit that's pretty simple and that we can test constantly, we can audit it. And finally, we don't want to take too long to generate that secret key, because until we have the key, we can't generate any random numbers, and that means, for example, we can't make a TLS connection. Okay, so look, here are our requirements. Let's get started. We're gonna design this circuit right here. All right, so where do we go? How do we generate random bits? Well, there are kind of two pieces to this. One piece is a noise source, the other is a conversion circuit. So the noise source is just some device, some physical device that has a phenomenon going on inside of it that's unpredictable. We'll talk about some specific examples. And a conversion circuit just observes that phenomenon and then puts out a bit as a result. So what are some examples of noise sources? Well, radioactive decay. We can watch sort of the timing between decay events in a radioactive material, or we could watch single photon interactions with a beam splitter, or we could use the photoelectric effect. But I mean, look, all of these are a little tough to put into an embedded system, right? I'm not gonna put a chunk of uranium in my embedded system, especially not now. But it turns out that circuit noise is a really, really good source of randomness. And in particular, every circuit device that you've ever used somehow has some random process going on inside of it. So for example, thermal noise, shot noise, flicker noise, Zener and avalanche noise. Well, okay, thermal noise isn't gonna be our best friend here. And the reason is that the magnitude of the thermal noise is proportional to absolute temperature. And remember, we wanna be insensitive to temperature, so that's a no-go. Shot noise and flicker noise, well, they're temperature independent to first order, but shot noise usually is pretty quiet, and flicker noise is strong at low frequencies, but not at high frequencies, which means we can't generate bits very quickly from it. But Zener and avalanche noise, now they're good sources. The reason is they're temperature independent, they're broad spectrum, they're quite loud, and they're quite easy to generate. In particular, the way that they come about is we just reverse bias a diode, and then it starts making noise. So in particular here, we're gonna concentrate on avalanche noise because it turns out it's a little noisier than Zener noise. So let's recall a little bit about how diodes work. All right, so normally we have a diode, we apply voltage in what we call the forward direction, and current can flow. But if we apply voltage in the reverse direction, then there's no current flow, right? All right, well, what happens if we put a lot of voltage in the reverse direction, right? Then we go into what's called reverse breakdown. The diode starts to conduct, even though it's supposed to be blocking the current. And there can be destructive reverse breakdown, but it turns out we can reverse break down a diode without destroying it, and that's what we're gonna be concentrating on here. So in particular, what happens is we get this effect called avalanche current. And so when we put enough reverse bias across the diode, there are these very energetic electrons that are kind of trying to fly through the diode, and they're gonna smash into other electrons. And when they do, those electrons are gonna be excited, and they're gonna smash into other electrons. And after we get enough excited electrons, then there are a bunch of charge carriers floating around in the diode, and they can conduct current. So this is how the avalanche effect works. And this is kind of a cool thing because it's like deeply related to like subatomic phenomena, like two electrons happening to interact or not. So as far as we know, this is a completely probabilistic process. There's no way to sort of externally decide, you know, when one electron will interact with another. And as a result, we get this current that's highly unpredictable. So let's take a look at what we mean. So here's a test circuit on the left. We apply a bias voltage of a little over 12 volts to a diode that'll break down with 12 volts across it. And then we measure V noise, the voltage on top of the resistor, and what we see is essentially the noise current. So on the top right, this is a graph versus time of what that noise current looks like. And what we're getting here is sort of 100 millivolts peak to peak across a 10K ohm resistor. So we're getting a decent amount of noise current here. And on the bottom right, I'm showing you a histogram of the values, so we can see that, you know, there is this kind of nice spread. I'm not showing you the spectral density, but it's essentially flat too. So great, we have this circuit. Can we just use this directly? Not quite. So here we had to adjust this voltage to just right to get the thing to work. And if I had taken a different diode and stuck it in there instead, well, that wouldn't have worked quite the same. So if I wanted to build 1,000 of these devices, maybe 200 of them would fail. So how do we get around that manufacturing tolerance? Well, we're gonna reach into the analog bag of tricks and pull out negative feedback. So what I've added here is an op-amp, that's in the blue box, an operational amplifier. And basically the op-amp is gonna look at the voltage on V noise, and it's gonna apply a voltage to the top of the diode that's just enough to get V noise to be, on average, equal to V ref. So the average voltage is being set by the op-amp, but the instantaneous voltage is still a result of the noise process from the diode. And so now we have this guarantee. We have this noise circuit that's gonna put out something that has an average of V ref. And now we can convert this to bits. So in particular, if V noise is higher than V ref, we'll call that a 1. Actually here, we'll call that a 0. And if V noise is below V ref, we'll call that a 1. And we're gonna do that using another analog building block called a comparator, which, as its name implies, just compares two inputs. So finally, this gives us some indication. V noise is either above or below V ref, kind of at random as a result of the noise process. And then we can sample that 0 or 1, and now we get a sequence of bits. We get a bit stream out of it. So we're done, right? Well, no, of course not. There are a couple problems here. Let's take a look at one immediately. So what happens if there's some disturbance that's being injected into the circuit from, say, the power supply? So for example, there's some capacitive coupling between the power supply and this V noise wire. So I'm modeling that here as just a disturbance current injecting there. Well, okay, so imagine in particular that the disturbance current is zero mean. So that means that the op-amp doesn't have to fight it, because on average, the V noise voltage is still correct. But instantaneously, the value on V noise is highly correlated to the value of the disturbance current. And that means that the output bits will be highly correlated to the disturbance. And now we don't know anything about those statistical properties, right? Because it may be that the disturbance current is highly predictable, and so we're stuck. The output bits are now highly predictable. This is no good. Okay, so we're gonna reach back into the analog design toolbox, and we're gonna pull out a differential circuit. Okay, so in the blue boxes now, I've instantiated two versions of the noise circuit, all right? And what we're gonna look at, instead of looking at V noise versus V ref, we're going to look at V noise 1 versus V noise 2, okay? So here's the reason that this is cool. So imagine again, we're gonna inject a disturbance current into V noise 1 and V noise 2. And in particular, imagine that it's the same current. right? It's the same value of current. So that means, let's say vnoise1 goes up by a millivolt and vnoise2 goes up by a millivolt, but their difference doesn't change, right? If vnoise1 was greater than vnoise2 before the 1 millivolt change, it'll be still greater than it after the 1 millivolt change. So this is great. We can reject any common mode disturbances. And so the question is, well, how do we make sure that all of these disturbances affect both circuits the same? And kind of as always, the answer is you gotta be careful about the way you actually physically build the circuit. So in particular, if we lay out the circuit in a way that each of the noise circuits kind of sees the same environment around it, well, then everything is okay. As long as they match very well, then they will see all of these disturbances as common mode, and they'll reject them. Okay, so we're getting there, but remember, we started out with this test circuit that needed 12 volts to break down one of these diodes, right? And yet we're in an embedded context where we maybe have a 3 volt power supply or a 1.5 volt power supply or something like this. So where are we gonna get this 12 volts from? Well, okay, standard answer, we're gonna add a boost converter, right? So this is a power converter that takes in the, say, 3.3 volts and puts out some value that's greater than 3.3 volts, say it's 12 volts or 18 volts or whatever. And this is a totally standard approach, and it completely solves our problem, and it completely adds a new problem. And the new problem is, the converter itself is very, very, I don't wanna say noisy because it's not noise in the same sense. It's going to disturb the circuit, but in a very predictable way. So in particular, anytime the M1 is turned on, there's this huge current dump through the inductor, and anytime we turn off M1, then that node flies around, and so there's all this capacitive coupling to kind of everywhere in the circuit, and it's a total disaster, right? So if we ran this as such, we would completely obliterate the noise that we really want to detect, which is what's coming out of our diode. So how do we fix that? Well, what we're gonna do is we're gonna have the boost converter, but we're not gonna run the boost converter when we're taking the measurement. We're only going to run the boost converter when we're not taking measurements. So we're gonna run the boost converter to charge up the output capacitor, and then we're gonna turn off the boost converter, and we're gonna let the output capacitor just support the circuit as it runs. So I'm gonna show you an example of that, and there's a lot here, but we'll walk through it. So the blue line is the boost converter's output voltage. And that gold weirdish line is the boost converter's input current. And finally, the green line is approximately the comparator's output, except that it's sort of at too fine a time scale for us to see the full logic levels. So, all right, let's walk through it. So about a division and a half from the left, we turn the whole thing on. And you can see the blue line starts to rise. And so the output voltage of the converter is charging. Now, about 4 divisions from the left, we turn off the boost converter, and you can see the blue line starts to sag. All right, in the meantime, take a look at the input current to the boost converter. So the input current is going all over the place, making all kinds of noise, disturbance, in that first portion. And then when we turn it off, it's completely silent. Everything's great. So now, as soon as we've turned off the boost converter, we can see that the noise circuit still operates for a while because the output capacitor has enough charge to support that operation for a few tens of milliseconds. And so in that time, we can sample the output and we'll be able to take some nice clean readings from our noise circuit. Great, so let's now put the whole thing together. So we know how to generate essentially unlimited random numbers as long as we've got a key, and we have a circuit now that lets us make that key. So let's figure out, what does the system look like? Well, there's kind of 2 phases. At boot time, we're going to generate the key, and then at runtime, we're gonna use it. So in particular, at boot, we're gonna turn on that circuit, and we're gonna gather 1024 bits, something like this, something conservative. And then we're gonna take those raw bits, and we're gonna run them through a cryptographic hash function, like SHA-256. And finally, we're gonna just initialize a global counter to 0. Okay, so why are we using this hash function? Well, it turns out that under reasonable cryptographic assumptions, the output of a hash function looks pretty much like random. And in particular, we can think of the output of the hash function as being sort of unbiased, even if its input is slightly biased. So what we're doing is we're distilling entropy out of the 1024 bits into 256 bits that are much whiter, okay? Which is to say spectrally flat. Okay, so now we have this global counter 0, we have the key k. And when now we actually want to generate a random number, we're going to increment the counter, we're going to encrypt the value of the counter, and we're going to return that ciphertext. And that's it. Very simple. Okay, so a couple comments. I said we want to be able to test this thing and we want to be able to audit it at runtime. We talk about this in some detail in the paper, but I want to give you an idea. There's kind of two phases to this. When we first build the device, we kind of go through some sort of heavy-duty testing just to make sure that all the pieces are working correctly. And then at runtime, we can apply some tests that are sort of health checks to make sure everything's kind of okay. All right, so let's take a look at some eval results. We're gonna ask here first, how quickly should we sample the generator's output? Remember, what we're getting from the comparator is just some bits, and then we have to sample them to create the bit stream. So now we have to make a decision. How fast are we gonna sample them? We're gonna look at some statistical properties of the raw bits that come out versus time and versus temperature. And we're gonna look at the total cost in terms of time and energy for generating a key. So first, what did we build? Well, so we actually built two versions of this thing. On the left is a standalone version. That's about 1.5 centimeters squared, but you can see there's a little room to be taken out of that, so it's a prototype. We'll get there. And it costs about $1.50. On the right is a full IoT embedded platform, and in fact, you can see this platform in action at the demo session later. And on the top right of that board, you can see almost the same layout. So in fact, they're scaled almost exactly the same. Okay, great. So first question is, how do we sample this thing? All right, so before we ran this experiment, we decided here's how we're gonna test this. We're gonna take the raw output and we're gonna run it through this test suite called the ENT test suite. And now you might say, look, earlier in the talk, we just discussed that we can't run statistical tests and get any certainty out of them. So what use is running these statistical tests? Well, here's the answer. We're not using the statistical tests to make sure that the noise source is okay. We believe device physics, and therefore we believe that the noise source is okay. We're using the statistical tests to make sure that the circuit is operating correctly. So if the circuit were bad, we would see really bad sort of low entropy output, even though we know that, of course, the behavior of the avalanche breakdown itself is highly unpredictable and highly probabilistic. All right, so the other thing to think about here is, all right, why is it that we have to worry about the sampling frequency? Well, okay, so the comparator that we use, it has some limited bandwidth, right? It's not a perfect device. And in particular, let's say its output can switch at maybe 10 megahertz or 5 megahertz or something like this. So what that means is if I sample very, very quickly compared to 5 megahertz, well then of course the output can't have changed, and therefore the two samples that I've just taken are highly correlated to one another. So before we even ran this experiment, we said, look, all right, if it's 5 megahertz, then probably if we give it sort of a 10x in terms of padding, probably about 500 kilohertz, there should be no correlation. We took the data, and indeed we see that up to a few hundred kilohertz, the correlation is very low, and after that, it kind of goes crazy. So we chose, conservatively, I'd say, 128 kilohertz as our sampling frequency. That's well below, 10x slower than the comparator can go. And that's what we'll use for the rest of the presentation. So next question is about the statistical properties. So on the top here, we see a measure of entropy. The units are sort of, it's kind of unitless, or bits per bit, if you will. So it's sort of the bits of uncertainty per bit of output. And what you see is that it's very, very close to 1. For kind of reference, if we use exactly the same statistical test suite on sort of previous designs, we get something like, 0.85 bits per bit or something like this. So we are much, much closer to 1, and this is a result of, being very careful about trying to eliminate correlation and this sort of thing. And the other thing to notice is that over a wide range of temperature, there's essentially no change in the amount of entropy, right? We go from 0.99 to 0.995 or 0.98 or something like this. Well, why is there any change at all? Well, look, as I said, all of these circuit devices have some thermal noise associated, some shot noise, et cetera. And they make very, very, very small contributions to the total entropy. So at cold temperatures, they're not making very much contribution, and so we're getting only the contribution from the diode. So that's sort of what we should regard as the amount of entropy that we're truly getting from the diode, and that's what we can rely on. The other question is, what does this look like over time? Is it gonna be, pretty good entropy for a long time? And so what we did was we took data. Every minute we took 1,000 sets of samples of 512 bits each, and we did this for about 10 days. And what we see is that, yeah, there's some variation over time, and some of it is actually attributable to temperature, But on the whole, we stay sort of above 0.985 kind of over long term. So again, we feel pretty comfortable that the circuit is operating correctly. So finally, how much does it cost? Well, remember we have these two phases. First, we charge up the converter, and then we let it droop as we sample the data. So it takes about 13 milliseconds to run the converter, and then it takes about 12 milliseconds to sample. So on the whole, we have 25 milliseconds at boot time, and that's it. That's all you have to spend with the hardware. And in terms of energy, it costs about 3 microjoules per bit. And as I said, that's about 10x more energy per bit than a Zigbee radio. So to gather these 128 bits, or sorry, these 1024 bits, it's about 10 Zigbee packets worth of energy. All right, so what should we take away? Well, first, I hope that you'll worry about where your random numbers come from, but that you'll feel confident that you could use a cryptographically secure random number generator as long as you have a key. In embedded systems, we need to worry about this key. And so using hardware that's specialized to that purpose, I think completely makes sense. We hope that you'll use our hardware, and to that end, it's open sourced. You can find it on GitHub. And with that, I'm happy to take any questions.
Any questions?
Hi. So really interesting work. I have two questions. The first is, given that your identified attack vector is that you don't trust the silicon vendor or you don't trust the fabrication of the chips and whatnot, how is this inherently more resilient to that attack vector? I mean, what if when it's being assembled, they replace the comparator, for example, or they replace part of the chip that is busy sampling your input or output from your circuit, for example? So that's the first half, and the second half is, given the complexity of trying to defend against that attack vector, why is this more secure than just relying only on mixing? So say flashing a device with a pool of entropy when you ship it, and then mixing in that entropy into your pseudorandom number generator.
Oh, thank you. Those are both very good questions. So in terms of why we would worry about this, or less about this than about, say, something that's, well, I'm sorry, there's kind of two pieces. First, why do we worry about this less than an integrated circuit that has the same functionality? Well, the reason is we know we can test this, right? I can put a scope on the parts of the circuit that I want to check, and I can be sure that they're okay. And in particular, we hope that there's some acceptance testing when we manufacture the thing to check that, in fact, these things are okay. But that immediately implies that we need to trust the manufacturing of the boards, right? That's somewhat separate from trusting the manufacturing of the integrated circuits that go onto the boards. Is that reasonable? Well, I guess the answer, as always, is it depends. But look, if you're going to integrate, a circuit, if you're going to use an integrated circuit that's in a reasonably modern technology, then you kind of have 5 manufacturers that you might be able to go to for that IC. Ultimately, like the fabrication house. And so it's not so hard to imagine that some or all of those are corrupted. On the other hand, it's not that hard to put together a circuit board. So kind of anyone can do it, and there are many, many circuit board building houses. So if we were really paranoid, we could just make our own circuit boards and at least control that portion of the supply chain, right? So in some sense, it's like we could take back some control over the supply chain. And now I'm just worried about, well, is my Zener diode really a Zener diode? Probably. I mean, a few billion of these things get cranked out every year. It's much harder to imagine backdooring a Zener diode for the evil purpose that like 1 in 1,000 people will stick one into a random number generator, right? So it's sort of a game of raising the wall rather than a game of saying, yes, now we're perfect.
Fair enough. And then the second part is, in your tests, if you can't trust the pseudorandom number generator, why not just mix the entropy, which is generally how people cope with entropy sources that are probably random but a bit suspicious?
Oh, this is a good question. So you're saying something like you could build the secret key in, just flash it into the device, and then you're done. Yeah. It's true. That's honestly, for some applications, that's probably a perfectly reasonable approach, right? And yeah, if I build in a 256-bit key, I should be able to use that thing essentially forever. So yeah, why not just put it on flash and call it done? Probably we could say that, look, if we're in a high security environment where we're actually doing these online tests constantly, then there is some difference between trusting that my flash hasn't been tampered with and trusting that, well, now my health checks look okay. That said, I understand that, well, okay, fine, if I can tamper with the flash for the bits, then I can also tamper with the code. So, yeah, it's a good question. That would be a reasonable approach, I'm guessing, in some situations too.
Cool, thank you.
Thanks.
How's it going? Here's Daniel from Colombia. So, for the power supply rejection, right, you're doing like take the difference from the two circuits, right?
Mm-hmm.
Is there any reason why not taking like a fully differential circuit? Like, wouldn't that like give you a better PSRR?
Well, I mean, this is essentially fully differential. I mean, it's not clear to me that we're going to, I mean, so you're saying something like, what would we want to make more differential here?
So, like, if those resistors are not exactly the same, or those OTAs are not exactly the same, then you're going to have like a...
Well, the op-amps probably we're not so, right? I mean, okay, if there's offset in the op-amps, maybe we wrap an integrator around it instead, life is okay. Resistor matching, I think, is always going to be an issue. Like somehow, when we're talking about matching, at the end of the day, we have to be able to come back to one component and say X equals Y, right? So generally speaking, for practical reasons, you want to match resistors and not say capacitors or op-amp gains or something crazy, right? Because at least resistors we can test and they're relatively stable over time and temperature. So yeah, I think there's no doubt that what I've called R2 and R3 here absolutely need to be matched. But I think I'm not so concerned about whether op-amp 1 is exactly the same as op-amp 2.
Yeah, okay, and the second question. So wouldn't the feedback loop also like take care of a little bit of your noise? So if you're...
Yeah, absolutely. So, I mean, there's something slightly imprecise about saying, well, we're going to set the average to X, but we're going to expect the instantaneous. I mean, clearly what that really is saying is something like out to the gain bandwidth product of the op-amp, the value of V noise is essentially equal to V ref, and then past the gain bandwidth product of the op-amp could do nothing, and so that's where the noise is really coming in.
Like the higher
So yeah, so it's really the high frequency noise that is what's being detected by the comparator here. So there are a couple solutions there. One, higher bandwidth comparator, life is okay. Two, I think I've already mentioned this, but just wrapping an integrator around this, or adding an integrator to this feedback loop. I mean, look, it makes the circuit diagram more complicated, but it's exactly the same, right? What we're doing is simultaneously we're killing any imperfection from low frequency gain issues, and we're killing the bandwidth of the op-amp, so that average out to the gain bandwidth now becomes average out to say 10 hertz or something.
And what about the other noises? Like you said, it's much smaller than the noise from the, how smaller? How much smaller it is? Like
You're saying like the
flicker noise from the...
Well, I mean, so the op-amps that we used, they're not even very good op-amps, and yet like the input referred noise is maybe a few nanovolts per root hertz. So like maybe a few tens of nanovolts per root hertz. But if you compare that to like the noise from that diode input referred to the op-amps is like 100 millivolts per root hertz. I mean, it's like, no, that's not right. 100 microvolts per root hertz. I mean, it's much, much, much bigger. So yeah, there's some extra effect from thermal noise, but this is engineering. It's zero.
Okay, thank you.
Hi, this is Miklos Murthy from Manabrit. Okay, so you have mitigated some of the design problems in successive steps. And how do we know that you mitigated all the problems? For example, electromagnetic radiation. For example, the wavelengths of equal to the distance between the two amplifiers. I mean, all kind of stuff I can come up with. And how do we know that you have actually checked any of these?
This is a very good question. So we discussed this in a little more detail in the paper, but there are some sort of underlying assumptions here. Obviously, I can't address everything, but in the particular case of radiation, if we're, look, in a system where we're concerned about this sort of thing, it's going to be trivial to shield this, right? So yes, this ends up being, you might argue, something like a cat and mouse game. Totally a fair argument. On the other hand, look, we could sort of enumerate the ways in which we can hope to influence the circuit, and we can try and squash those. And I think something like assuring physical security of the circuit, which is kind of an umbrella for all of these things, well, at the end of the day, we're going to need that physical security anyway. If the device is going to be generating, say, a TLS key, well, if you can poke the memory in the device, then all is lost, no matter how good the randomness is, right? So in some sense, we can call the physical security of the device an orthogonal problem. And yes, there are good solutions to it, but we can solve those separately from the problem of generating random numbers.
Okay. okay, if the physical security of the device is a solved problem, then you know usually, I mean, you need randomness to communicate. And if you can communicate, and then you can store some private key in the device. So essentially what you're doing is you're replacing a security based on mathematics with security based on some hardware design, and we have absolutely no idea how this hardware is actually going to behave. Would you trust all the iPhones in the United States on this security?
Well, it's easier to answer the second part of that question than the first.
You would not.
Of course.
Thank you.
Okay.
Thank you.
Due to the time limit, we're gonna stop here. I'm sure Riyad is gonna stay around after the session, so go ask him questions.